This conference will now be recorded.
Hello everyone. We'll start with the problem, this problem, and there will be another problem, and after that there will be discussion related to stability of complexes, then stability constant. There are also overall stability constant and stepwise stability constant and related problems. And after that there will be Chelate effect, macrocyclic effect, and if time permits, then effective atomic number calculation we will see. So match the complex ions that are given in column 1 with the hybridization and number of unpaired electrons that are given in column 2. So in the second column, there is mention of the hybridization of each of these complex and also the number of unpaired electrons. So these numbers that you are seeing here, all these are number of unpaired electrons. So we have to match this. We have total 4 items in the left hand side, but 5 items in the right hand side. That means 1 will be extra. Fine. Now the first one is chromium H2O whole 6 3 plus. Now water is neutral ligand. So the charge that is present outside the coordination sphere, that is actually the charge of chromium. So it is having +3 oxidation state. So chromium, when it is neutral, it has configuration after argon 3d5 4s1. So when it is in +3 oxidation state, now it will be having configuration 3d3 because 3 electrons are lost. So if it is 3d3, then the 3 electrons we can arrange in this way. Okay, then we have 4s and after that 4p. Now as it is 6 coordination, so 2 types of hybridization must be there. One is either d2sp3 or sp3d2, but in this case we have 2 d orbitals vacant in 3d, so d2sp3 hybridization that is possible. So if it is d2sp3 which is matching with 3, right, it is matching with 3, and also a number of unpaired electrons, it is 3. N is 3 here. Now if A is matching with 3, option B and D, these two cannot be correct because only A3 mentioned in option A and C. Now the next one, cobalt cyano, 4 cyano and then 2 minus. Now cyano is having -1 charge, so 4 cyano means total negative charge -4, and outside it is 2 minus. That means 2 negative charge that will be balanced by cobalt. So cobalt must have oxidation state +2. Now cobalt, when it is neutral, it has configuration after argon 3d7 4s2. So when it is cobalt 2 plus, it is 3d7. Now cyano is strong field ligand, so pairing is possible. So this is 3d. Fours 4p. So how we will arrange these 7 electrons? Now if you simply arrange it 1 1 in all the 5 orbitals, then 2 will be remaining extra, but there will be pairing, and pairing will occur in such a way because it is having coordination number 4, so it must be either tetrahedral or square planar. Now pairing will occur in such a way that only here you need 1 d orbital because square planar means it is dsp2 hybridization. Now 7 electron dsp2 hybridization, sorry, p2. So if it is dsp2, that means square planar, and how many unpaired electrons are there? Only 1. So it is matching with, B is matching with 1. That means among option A and C, B is 1 that is present only in option A. So this much information is enough to choose the correct answer. Sometimes it may happen that you don't have to go through all the complex, and it will save your time also, fine. But here we'll see the other 2 complexes also. The next one, C, nickel complex, ammonia is neutral, so oxidation state of nickel is 2 plus. Nickel when neutral, after argon it is 3d8 4s2. That means when it is 2 plus, it is simply 3d8 system. Now for 3d8 system, this is 3d. Coordination number 6. That means either D2sp3 or sp3d2. Fine. Now D2sp3 it is already taken by A. That means you have only one option left, which is sp3d2. So this is 4p and total 8 electrons. So 8 electrons, 5, then 3 more. Okay, so you have unpaired electron 2 and here hybridization will be sp3 and then 2d will be taken from 4p. So it is matching with 5 sp3d2 and 2 c5. And the last one MnF6 4 minus, manganese attached with 4 fluoride, that 6 fluoride and outside charge 4 minus. That means the oxidation state of manganese is Mn. Now Mn when neutral, it is 3d5 4s2. So when it is 2 plus, it is 3d5 system. Okay, F is weak field ligand and as it is 6, that means either sp3d2 or d2sp3. Fine, but pairing will not take place. If you have any doubt in any of these complex, total 4 complex are there.
No, ma'am.
So 5 electron like this, and there will be sp3d2. That means it is outer orbital complex. We also have to take orbital from 4. So sp3d2 unpaired electron 5 is matching with 2. So this is D. So keeping all this A3, B1, C5, D2, this will be the correct option. So one is extra here, which is 4, sp3 and 4. That is here extra. Okay, we have not used it. So if you have no problem, doubt in this problem, next we will see another one. Choose the correct statement. There are total 4 statements. That means only one of the statement will not be correct. Square planar complexes are more stable than octahedral complexes. Okay. Then spin only magnetic moment of CuCl4 2 minus. It is given 1.72 Bohr magneton and it has square planar structure. Then crystal field splitting energy Delo value for FeF6 4 minus, it is higher than the cyano complex. So here metal is same, ligand is different. And the last one, crystal field stabilization energy, that means CFSE of vanadium aqueous complex higher than the CFSE of titanium aqueous complex. Now the first statement, it may be that it is not always easy to understand whether it is really true or not, because square planar complex are more stable. We have already discussed that octahedral geometry is more having Delo value higher than tetrahedral, but no such stability related things we have discussed, right? So if you have doubt in the first statement, just keep it like this, because if you are sure about B, C, D, so obviously A will be incorrect. Fine. Sorry, we have to choose correct. That means if it is the correct statement, the other 3 must be incorrect. But if you find any of these B, C, D as correct, so obviously the rest of the 3 will be incorrect. So if sometimes it may happen that any option, if you have doubt, just keep it like this and go to the next one. So here we will directly go to B, and it is saying spin only magnetic moment of copper chloride complex 1.732. That means root over n into n plus 2. This is equal to 1.732. From this, you have to find out number of unpaired electron, which is very valuable information to understand the geometry. Now, number of unpaired electrons, that is n, this is always a whole number. It may be either 0, 1, 2 like this. Now, if it is 2, then it is 2 into 2 plus 2. That means it is root 8. Now root 8, it is not that is okay. Let me say, if n is 2, it is root 8. If n is 3, now it will be 3 and 5, that means 15. When n is 1, it is 1 and 3, that means root 3. Okay, now this will be slightly lesser than 4, because the next number root 16 is 4, so obviously root 15 is slightly lesser than 4, and this will be slightly lesser than 3, and this will be slightly lesser than 2, because the next number is root 4. So it is, see, close to this one. That means here n value is 1. So without calculator also you can understand here number of unpaired electron is only 1. Now if that is the case, that is copper Cl4 2 minus, oxidation state is 2. Now keeping this information in mind that it has one unpaired electron, just arrange all the electrons. Okay, one thing I forgot, Cu2 means it will have configuration 3d9, because when it is neutral it is 3d10 4s1, so 2 electrons lost, now it is 3d9. So here 9 electrons are placed, so see, only one unpaired electron is there. That means here square planar geometry, that is not possible, right? Because square planar geometry, if you want to get, there must be dsp2 hybridization, but it is from this electronic configuration, it is clear that it has to undergo sp3 hybridization, because there is no such orbital vacant in D. So that is why it means this is incorrect. Okay, this is false. Now the next one, crystal field stabilization energy, that is del O value for FeF6. So see here everything is same, metal is same, ligand is different, and oxidation state, that is also same. Here it is +2, this is also +2. So all this same, only ligand is different. Now cyano and F, if you compare its strength, obviously cyano is strong field, stronger than F. So this del O value, it is dependent on ligand. Remember spectrochemical series. So del O value for the cyano complex will be high, not for fluoride complex. So this statement, which is saying that CFSE, this energy is greater for FeF6 complex, that is not correct. Fine. And the last one, crystal field stabilization for vanadium H2O6 plus. Now vanadium H2O6 plus, here oxidation state of vanadium is +2, and oxidation state of titanium, that is also +2, because water is neutral, right? Okay, before going to this, first I will write here the electronic configuration for vanadium. Vanadium when neutral, it is, remember, first one is scandium, then titanium, then vanadium. That means it will have 3 electrons, 4s2. So when it is 2 plus oxidation state, it will have 3 electrons. Similarly, titanium when neutral, it is 3d2, 4s2. So when it is 2 plus, it has 2 electrons, right? Now if you arrange it in Eg and T2G, then what will happen? For vanadium, here the calculation is mentioned. So for vanadium complex, three electron. For titanium complex, 2 electron. So in the first case, it will be 3 into minus 0.4 del O, and for the titanium, it is T2G2, which is 0, it is 2 into minus 0.4. So look at these two values. Here, whenever you will say it is mentioned that CFSE value high or low, you have to focus only on the numerical value, not considering the negative sign. Because if you consider the negative sign, then minus 0.8 is greater than minus 1.2. But if you consider numerical value, 1.2 is greater. Okay. So here this statement is basically correct, because for the vanadium complex, the CFSE value is high because it is 1.2, which is greater than 0.8. So this statement, the last statement, is correct. Now when you are sure that D is correct, obviously if you have doubt in the first statement, it has to be false. Okay. And truly speaking, square planar complexes are more stable. There is no such thing that always it will be keeping all the other factors same. That is, if you have kept metal same, ligand same, oxidation state same, you have changed only the geometry. In one case square planar, another is octahedral, then it will be more stable. There is no such thing. It may vary. Sometimes it may be that it is more stable, sometimes it may not. So it is not always true. So keeping all this in mind, the correct statement is the last one. So any doubt? Should I repeat? Next new topic is stability of complexes. Now when we are talking about stability, there are two types of stability. One is thermodynamic stability, another one is kinetic stability. Now thermodynamic stability, it is about how, okay, let me first consider kinetic stability. It's easy to understand. Kinetic stability means it will form very fast, but that doesn't mean it will be stable for a long time. When you are trying to make this complex, it will be produced very easily, that the speed is very high. But if it is thermodynamic stability, maybe it is not produced at a very high speed, but once it is formed, now it is stable. So this is the difference between these two, thermodynamic and kinetic. Kinetics is all about speed, how fast it will form, and thermodynamic is that with time, which one is more stable. Maybe it is formed in a very less amount, yield is very low, but it is very stable. Okay, so thermodynamic stability, it is actually related to equilibrium, or you can say free energy change, del G, of a complex formation reaction. So when you are making a complex, suppose you have taken a metal and you are adding 6 ligands and you are getting Ml6. So for this reaction, obviously there is some free energy change value. So this del G value is related to this thermodynamic stability. And thermodynamic stability, it is measure of extent to which the complex will form or will be transformed into another species under certain condition when it is already reached equilibrium. So when you are making M, you have taken M6 ligand and there is equilibrium, you are getting Ml6. So the measure of extent to which the complex will be formed, that is the amount of Ml6 that will be formed. We are not concerned about how fast it is formed. We are just concerned about the fact, the extent, measure of extent to which the complex will form. When we are concerned with this type of stability, then we mainly deal with stability constant. So stability constant, which is denoted by beta, we will discuss it in detail. Remember, it is related to thermodynamic stability, not kinetic stability. And also metal ligand bond energy. So if metal ligand bond is very strong, so obviously this metal will be thermodynamically very stable. But if it is not very strong, then it will go back to left hand side. Okay, so it is not thermodynamically stable. Next we will see kinetic stability. So this refers to the speed with which this change, that is from left hand side, when you have simple metal with any oxidation state or zero oxidation state, I am mentioning here N plus. So from left hand side, how quickly you can move towards right hand side, that is the speed with which the transformation leading to attainment of equilibrium. That means how fast the equilibrium will be achieved. On the basis of kinetic stability, two scientists Tobe classified, there is another scientist also, classified the complex into labile and inert. So we are not going into detail, just remember, if a complex is kinetically very stable, that means it will be inert. But if it is kinetically unstable, it will be labile. Now labile complex means, suppose once it is formed, as it is labile, that means it is not kinetically stable. So what may occur? Suppose you have added another ligand L prime. So immediately Ml bond, that is Ml6, will be converted to Ml prime 6. That means it is now labile in nature, where in presence of other ligand it can exchange the ligand. And if it is not doing so, then it will be inert. Ligands of labile complexes are easily replaceable with ligands of inert complexes. Okay, sorry, it is mentioned that ligands of labile complex easily replaceable, but obviously if it is inert, it is the reverse, that is now you cannot replace it easily. So it is kinetically stable. Okay, So kinetic stability when we are discussing these two terms arises. Remember, these two terms are not applicable for thermodynamic stability. It is only for kinetic stability. But if you are concerned about thermodynamic stability, now you can talk about stability constant, metal ligand bond energy, or del G value, etc. Okay, so this is the difference. Now we will mainly focus on the stability constant. What is this? Remember, it is related to thermodynamic stability, which is denoted by beta. It is also known as formation constant because you are forming the complex. It is basically the equilibrium constant for the formation of a complex in solution from its constituent metal and ligands. So this is the definition. So see here, we have taken copper 2 plus metal. In presence of 4 ammonia, we are getting this metal. So here equilibrium constant, how we will express? Obviously the concentration in the product side divided by concentration in the reactant side. And as there is coefficient 4, so power is 4, but for copper there is 1 as power. So this is basically denoted as beta. There is a specific term for this. Otherwise it is nothing but the equilibrium constant for the formation of this complex from the metal, free metal and the ligands. Okay. The stability of a coordination complex, it is a measure of its resistance to replacement of one ligand by another. Okay. Now in case of kinetic stability also we have discussed this thing, but don't be confused between these two, because replacement, when we are considering in kinetic stability, that is related to how fast the replacement will occur. But when we are talking about replacement in this case, we are talking about the possibility. Is it possible that the ligand will be replaced by some other ligand L prime? We are not talking about how fast the replacement will occur. We are just talking about whether it is possible or not. So higher is the value of this beta for a complex, greater will be the stability. So if beta value for this copper amine complex, suppose if it is very high, that means if you are further adding some other ligand, it will not be exchanged. There is no such possibility. Fine. But if it is not so stable, that is beta value, if it is very less, now though it is a relative term, that is when we say less, there must be some range. If it is crossing that range, then only we can say stable. If it is less than that, then we can say unstable, right? So that we will also see what is the exact value above which, if we have the value for beta, then only you can say that it is thermodynamically stable, otherwise not. In aqueous solution, when the complex ion is dissociating, now consider the reverse reaction. Suppose you are moving from right hand side to left hand side. That means it is dissociation, it is not formation. So that is also another type of reaction, the reverse reaction. When complex ion is dissociating, there will be equilibrium between undissociated complex ion and dissociated ions. Now for this reaction, that is for the reverse reaction, here also we have equilibrium constant, but now the term is different. Now it is called instability constant because it is the reverse. Higher is the value of beta, lower is the value of alpha, because these two are inversely related. Beta is equal to 1 by alpha. Remember, suppose you are doing any reaction, reactant to P, that means R to P, product. So for this, if equilibrium constant is Kf, that is forward, and for the backward process, if it is Kb, so obviously Kf and Kb are related by this inverse relationship. So same thing is also here. But now the term we are using instability constant or dissociation equilibrium constant. Fine. So the reciprocal of this dissociation equilibrium constant, that is actually beta or vice versa. That is beta is equal to 1 by alpha or alpha is equal to 1 by beta. Both are same. So see this equation 2, this is basically the reverse of equation 1. Now we have written first the complex, and as if we are dissociating it to metal, free metal and ligands. Fine. Is it clear the difference between beta and alpha? Now there is another term that we have to learn is stepwise formation constant, overall formation constant. So the beta that you have just seen, that is basically overall formation constant, because it is not necessary that just in a single step all the 4 ligands or 6 ligands directly attached to the metal. It may not be so. It may be stepwise reaction. That means just look at the previous reaction. Here copper is attached with 4 ammonia. At a first glance it seems it is a single step reaction, but it may not be so. I'm trying to say, suppose copper is first attached with 1 ammonia, so you are getting the first step. Then this complex, that is CuNH3, only one NH3, it is attached with the second molecule of ammonia. So this is the second step. So in this way there will be total 4 steps. So for each of these single step there will be a particular stepwise formation constant. So that is actually the stepwise constant. When a free metal ion is in aqueous medium, it is surrounded by obviously water molecules. So here we have mentioned it MS6 because S is solvent. Now because metal, though in the previous slide we have written copper 2+ as if it is free, but when you are considering aqueous solution, by default you have to consider it is copper associated with water, because it cannot be remaining in free form in aqueous solution. It must be surrounded by water molecule. So that is why we have written MS6. If ligands which are stronger than water, if it is stronger, that is metal ligand bond stronger compared to metal water bond, then only the reaction is possible. So if you are adding such type of ligand to this aqueous solution, now coordinated water molecules will be replaced by this new ligand that you have added. So this beta that you have seen in the previous slide, this is actually beta overall stability constant. So see here we have written this equation as if this is metal ion surrounded by 6 S molecule, that is solvent molecule, now 6 ligands, and it seems as if it is single step reaction. So beta overall we have written as Ml6 S to the power 6, that is water molecules or any other solvent, mostly it is water. And here in the denominator we have the reactant side, all the species that are present. But as solvent is present in large excess, so you can easily neglect the S to the power 6 term. So ultimately it is simplified to in this expression that you are seeing here. Now look at this, total 6 steps are there. One, when MS6, only one S is replaced by L, and the corresponding stepwise formation constant is MS5L divided by MS6 and L. S is neglected because it is present in large excess. Now for the second step, it is now the product in the first step that will be treated as the reactant in the second step. Product in the second step will be treated as the reactant in the third step. In this way, there will be total 6 steps. If it is 4 ligand, it will be 4 steps. So finally what you are getting? You are getting Ml6 divided by the reactant site concentration, right? Now look very carefully at all these K1, K2 up to K6 values. Suppose if you are multiplying all these values, so what you are doing, you are multiplying K1 into K2 into K3 up to K6. So see, the denominator that is MS5L in the second step, when you are multiplying K1 and K2, this will be cancelled by the numerator. Similarly, here MS4L2, that will be cancelled in this. So in this way, ultimately the remaining value, what you will get, this Ml6, it will not be cancelled, and this in the denominator, this MS6 and L, that will also not be cancelled. So basically, when you are multiplying all these K1, K2, etc. values, what you are getting beta overall. So all these are known as stepwise stability constant, and beta overall is equal to if you multiply all this, it will be equal to beta. Is it clear how we are reaching at this relationship which is mentioned in the purple box? So it is not necessary it will be always 6, depending on how many ligands are there. And if you want to express it in general form, you can also write it as if beta is equal to K1, K2, dot 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 up to K. So it is in general, it may be any number of ligands. If it is 4, you will stop here, right? So I hope there is no doubt. Now in this table, in this slide, you are seeing general expression for all these K1, K2, K3. But now actual example we are seeing where copper. Remember this equation that we have already discussed. This is the beta overall. It is also mentioned as beta 4 because total 4 steps are there. And individually, if you write, then for the first step, see, only one ammonia is there. Actually, copper 2 plus is written, but ideally it should be written like this. That is copper H2O all 4 2 plus. But for simplicity, it is written in this way. And copper NH2 plus, then this is the starting material in the next step. Then another ammonia is inserted. Now it is CuNH3 whole 2, and ultimately it is CuNH3 whole 4. So if you are adding, not adding, if you are multiplying K1, K2, K3, K4, you will see that CuNH2 plus, this term is cancelled with this. Okay. So in this way, ultimately, it will be reduced to the value of beta 4 only. This relationship. Now here from experimental values, all these log K1, K2, K3, K4 values are mentioned. That is, I'm talking about all these stepwise equilibrium constant, and their log is taken. So these are the values. Okay. Now see, if you take log beta in the left hand side, it will be log K1 plus log K2 plus log K3 up to log K4. So that is why if you want to know log beta 4 value or log beta, just add all this because these values are given here. And this is equal to 11.9. That means here base is 10. So beta 4 will be equal to 10 to the power 11.9, which is almost equal to 10 to the power 12, 11.9, 12 approximately. So see, this value is so high, 10 to the power 12, which is very high value. That means this complex is very stable thermodynamically, obviously. Now remember, as I have told, that how you will understand a particular complex, is it thermodynamically stable or not. So if the value of log beta, that is the overall stability constant, if it is greater than 8, so see, this value is greater than 8 log beta, then the complex will be thermodynamically stable. So greater than 8 means what? Beta is greater than 10 to the power 8. If you are taking log, then it is greater than beta. But if you are removing log, it is greater than 10 to the power 8. In our case, it is 10 to the power 12, so which is obviously greater than 10 to the power 8. So that is why it is easy to understand that this complex is stable, thermodynamically stable. So is the calculation clear? Should I repeat? Here we have some examples in this table. So in the left hand side column, we have FeHCN2 plus, then copper 4 ammonia 2 plus, AgCN2 minus 1, cobalt NH36 3 plus, and AgCN4 2 minus. And the corresponding beta value is given, also alpha value is given. So beta and alpha, you know, these two are inversely related to each other. So that is why, see, when beta is 10 to the power 3, it is obviously 10 to the power minus 3, right? Now from these values of beta, can you tell me which complex is having maximum stability? Is it possible to mention? Just look at the values and try to understand in which case beta value is maximum. Look at the power especially. This is 3, this is 12, this is 18, this is 35, this is 41. So in which case beta is maximum, because maximum beta means maximum stability. And if you are considering it in terms of alpha, then minimum alpha value, that is actually the indication that it is maximum stable. So higher is the beta value, more is the thermodynamic stability, lower is the alpha value, higher is the thermodynamic stability, because alpha is inverse of beta. Any doubt? So here maximum value is Mercury complex, because maximum power you can see 10 to the power 41, and the least stable complex is the first one. Here iron is having +3 oxidation state, 1 SCN which is having negative charge, so outside charge is 2+. Fine, and this is 82. So this is minimum stable, this is maximum stable, which is clear from the value. Any doubt? Here we have a problem. Calculate the ratio of Ag plus concentration divided by AgNH3 whole to, it will be plus concentration in 0.2 molar solution of ammonia. If the stability constant of silver amine complex given 1.7 10 to the power 7. So basically here you are making silver amine complex starting from Ag plus ion and ammonia, 2 ammonia, and you are getting the complex AgNH3 whole 2 plus, because ammonia is neutral. So this is the reaction going on. Here ammonia concentration is given, fine, and the stability constant that is also given. From this information you have to find the ratio of free metal ion, that is solvated metal ion, divided by the metal complex concentration. So here beta is equal to, if you consider this reaction, first write the concentration term of silver amine complex divided by Ag plus concentration, ammonia concentration to the power 2. Now this value is given 1.7 10 to the power 7, and ammonia concentration is also known. Only this part is not known. So from this calculation you can find out the ratio, that is this ratio, the value you can get, which is this one. But we need the reverse of this ratio. See here Ag plus is in denominator, but we want Ag plus in the numerator, and here below there should be the complex concentration. So if this is the value of this ratio, obviously when you will take the reverse, it will be 1 divided by 0.068 10 to the power 7, and ultimately the value is 14.7 10 to the power -7. And this is, you can easily understand, because here beta value is very high, 10 to the power 7. That means the amount of the complex formed, that will be high, and remaining amount of Ag plus, that will be very low. That is all the reactants almost converted to proton. So now when you have taken Ag plus part, so obviously the concentration of Ag plus, it is much less than the denominator. So that is why the value is so low. It is very low, right? Which is also another proof that you have done the calculation properly. Okay, just check if there is no such options and you have to directly find the answer. Just check it whether it is correct or not. That is not exactly, qualitatively is it possible or not. So is the doubt clear? Should I repeat? Now this is an integer type of problem because you have to find a plus b, where overall formation constant it is mentioned in this format. Okay. Now integer type of value means it will be a whole number. A and b will be whole number. Then you have to add these two values. Ethylene diamine, that is En, NH2, CH2, CH2, NH2, displaces water molecule in this iron aqueous complex in 3 steps. So see, it is hexa-coordinated and 3 En we have taken because per En there are 2 donating sites. That means when all the water will be replaced, 3 En, it is basically fulfilling all the 6 coordination sites. So 1 En when will be inserted, 2 water molecules will be outside. So total 3 steps. In each step 2 water molecules will be removed. So total 6 water molecules. Now as it is 3 steps, so all the log K1 value, log K2 value, log K3 value, all these are given. Now we know that beta, that is overall stability constant, that is K1, K2, K3. Now if you take log beta, then log K1 plus log K2 plus log K3, that means just add all these values, right? So if that is one way you can do, that is you have taken log beta and just add 4.34, 3.31, 2.05, and ultimately what you will do, suppose there will be some value particular, so next beta will be 10 to the power, so suppose if it is x, it will be 10 to the power x. So this is one way you can do. Another way is log K1, if it is 4.34, that means K1 is 10 to the power 4.3. So now use this equation, the first equation. So now beta will be equal to K1, that is 10 to the power 4.34 into 10 to the power 3.31. See, here beta is written in terms of only K, as if this is beta, right? K, beta or K. So just multiply all this. This is another way you can do. Actually, you will reach the same answer. So this is basically 9.7. Okay. So 10 to the power 9.7. If you do the calculation, it will be 5 into 10 to the power 9. That means now if you compare with this, A is basically 5, B is basically 9. So A plus B, it will be 5 plus 9. That means 14. But in this problem, there is one error, which in my opinion, it shouldn't be framed in that way, because this 5 into 10 to the power 9, you can also write it in this way, right? 50 into 10 to the power 8. Now in this case, A will be 50 and B will be 8, right? That means now you are getting completely different results. So this is one problem that I have found in this particular problem, which is integer type of problem, but it is it came in exam as it is, fine, and this is the answer that is reported, but there may be so many values in my opinion, fine. Next one, what is the ratio of uncomplexed to complexed Zn2 plus? That means uncomplexed, first you will write, that is Zn2 plus, divided by complex, that means Zn ammonia whole 4 2 plus. So this ratio you have to find in a solution where concentration of ammonia is given, stability constant is also given. So see, this problem you can find similarity with the previous slide. There was also a problem, I'm talking about this last problem. Here also it is same thing. Basically you are finding the ratio Ag plus, which is uncomplex, divided by the complex form. Ammonia concentration is given, stability constant is given, you just have to find the ratio. So same thing here, right? Now these are the options. In the previous case there are no options, but now there is option. Stability constant 3 into 10 to the power 9. So obviously this it means what? Beta is very high, so this is very stable complex. So it is in the right hand side, right? Now if it is very high, obviously Zn2 plus is very low. So this numerator is very low than denominator. So obviously all these will be negative. So see, all the options there is negative. So just on the basis of this discussion, you cannot choose right option. You have to do the calculation. So this is the equation. Zn2 plus reacting with 4 ammonia, there is equilibrium. You are getting zinc amine complex. This is Kf, or you can say it is beta, and this value is given. Ammonia is known, 10. So 10 to the power 4, because ammonia concentration to the power 4. So this reverse of this ratio you basically need. So see, this is the ratio, 10 to the power 4 multiplied by 3 into 10 to the power 9. But we need the reverse of it. So obviously 9 and 4, it is almost 11. And if you take reverse of 3, 1 by 3, then ultimately 10 to the power minus 4. That is, it is arranged in a different way. Fine. So power, it is basically 1 by 3 into 10 to the power 30. Fine. But it will be 0.33. So 0.33 10 to the power minus 13, you can write it in this way, because you have to match with this. Fine. So it is matching with option C. Any doubt? Should I repeat? Next is Chelate effect. Now remember, we have discussed different types of ligand: monodentate ligand, bidentate ligand, tridentate ligand, and polydentate ligand. Okay, even hexa-dentate ligand, very good example is EDTA, ethylene diamine tetraacetic acid. Now in case of monodentate ligand, look, suppose L is monodentate. So two ligand attached to metal, there is no formation of ring. But if it is bidentate ligand, so it will be attached with metal like this, and there will be formation of ring. But in monodentate, there is no such ring. And depending on how many number of atoms are present in this, because it is the general expression, depending on that, ring size also will be different. It may be 5-membered, 6-membered, like this. So the main thing that is we should notice here is that if it is monodentate, there is no ring. If it is at least bidentate, if it is tri, penta, tetra, then also ring formation will be there. But minimum, it must be bidentate. When a ligand attaches to a metal ion in a manner that forms a ring, then the metal ligand association is found to be more stable. So ring formation, when takes place, the complex is having more stability. What is the reason behind it? That is related to entropy. We are coming to that point. First, be clear about this fact. Whenever there is ring formation, the stable complex is more stable. So the complexes containing chelate ring, these rings are known as chelate ring, and the process is known as chelation. Fine. They are more stable than complexes without rings, and this effect, that is the stabilizing effect, that is known as Chelate effect. So sometimes you may find question where it will be mentioned that in which case Chelate effect is possible. So what you have to do, it is very easy. You just have to check whether the ligand is monodentate or at least bidentate, because if it is monodentate, ligand Chelate effect is not possible. Now this is why this stability is arising when there is chelate formation. It is because of entropy factor. Now look at this example. This is equation number 1. This is equation number 2. In both cases, we have taken same chromium ion associated with 6 water. Fine. Now, in the first equation, we have taken 3 oxalate. Now, oxalate is bidentate. Here, coordination number is 6. To satisfy coordination number 6, oxalate ion required 3 molecules, because per molecule to rotating side. So see now the formula, CrC2O4 3 to the power 3. and all these 6 water molecules are removed. So when it is once the complex is formed, how many particles are present in the right hand side? 1 complex and 6 water, that means total 7 particles. And in the left hand side, 1 chromium ion with water and 3 oxalate, that means 1 plus 3, it is 4. That means the difference between this number is 3, 7 minus 4. So entropy is increased because higher is the number of particles, randomness increases. So del S is positive because from lower number you are getting higher number. So entropy is positive. Now in the second equation, same chromium, but now instead of C2O4 we have taken EDTA. Now EDTA itself is hexa-coordinated. So a single EDTA molecule is enough to satisfy all the 6 coordination sites. So that is why now 1 EDTA we have taken and 2 particles, 1 plus 1. And in the right hand side, 1 complex, 6 water, again 7. But now take the difference, 7 minus 2, it is 5. So it is true that in both cases del S is positive, randomness is increasing. But in which case it is more increasing? Obviously the second one, 4 to 7 and 2 to 7. Obviously 2 to 7 is more randomness increase. So that is the explanation that the more binding groups a ligand contains, that is if it is compared to mono in bidentate, obviously rooting site is high, more positive will be del S. Similarly, if you compare between EDTA is hexa-coordinated, C2 oxalate is 2 coordinated. That means when you are moving from bidentate to hexadentate, then also entropy is increased. That means in both cases chelate formation is possible. But in which case it is forming more stable chelate? It is obviously the EDTA complex. Why? Because of this del S value. So if it is asked in which case more stable complex is produced, just check how many particles are generated from how many particles. It will give you the answer directly. Another example. Now this is comparatively simple. See, cobalt water 6 water 2 plus, cobalt water 6 water 2 plus. Equation 1, equation 2. What is the difference? Here we have taken 6 monodentate ammonia. Here we have taken 3 bidentate ethylene diamine. So here you have how many particles? 1 plus 6, 7. This side 1 plus 6, 7. That means del S is 0. In this case 1 plus 3, 4. And here 1 plus 6, 7. So now 7 minus 4, it is 3. So 0 and 3, obviously the second one is giving you more chelate effect, right? The equilibrium constant, it is found that the equilibrium constant for the second equation, it is 10 to the power 5 times high compared to the first reaction. That means K2 divided by K1, it is 10 to the power 5. So see, just by changing the monodentate ligand to bidentate, there is so drastic difference in the value. So this is cobalt ethylene diamine complex. You can see 3 5-member rings are generated. This is also a very common type of question. That is, a molecule complex will be given and it will be asked how many rings are formed. And it may be also another type that how many 5-member rings are formed or how many 6-member rings are. So you just have to draw the complex and you will get your answer. Fine. So why it is 5-member? Because N, C, C, N metal. But here there is no ring. So is there any doubt? Chelate effect is clear. Should I repeat? Next is macrocyclic effect. Now you may find some similarity between Chelate effect and macrocyclic effect because basic principle is same, but it is not same. Otherwise, there should not be any different term that we are using. These two are not same, right? So it is the increased thermodynamic stability of a complex formed with a cyclic polydentate ligand. So in the previous case, what we have seen, we have just taken polydentate. It is not necessary that the ligand must be cyclic. Remember, we have taken ethylene diamine or oxalate, they are not cyclic. They are bidentate, but they are not cyclic, right? But in this case, try to understand the difference. It is not just polydentate, it is also cyclic. When compared to complex formed, that is keeping the metal same. Now just you have taken the open chain form, non-cyclic. This is also polydentate, but it is not cyclic. Now look at this picture. A, obviously it is polydentate. If you keep metal here, it will bind from four sides. B, that is also polydentate. That is, this is also tetradentate. But what is the difference? Here it is open, but here it is attached. So this is cyclic ligand. B is cyclic, A is not cyclic. So Zn2 plus, when it is complexing with the first ligand, then the del G value is minus 64. In the second case also it is minus. But we know higher is the, that is more negative is del G, more will be the stability. So that is why this complex is more stable than the first one. Okay. Now, why it is happening? That why you are getting more stable complex when you have taken some cyclic ligand? Try to understand the reason. Macrocyclic effect follows the same principle as the Chelate effect, but the effect is further enhanced by the cyclic conformation of the ligand. So see, here if you look at A, though I have written A in this way, as if it is already pre-arranged, so that it can bind with metal very easily. But suppose, if I am drawing it like this, suppose I am writing the same A molecule, but slightly different way. NH, then CH2, CH2, NH. So if I am writing the molecule in this way, sorry, there are 3 carbon. 2 carbon, then 3 carbon. Then again 2 carbon. Now if the metal, that is zinc, if it is here. Now see, this NH2 site, it is very near to Zn. But this NH and this NH2, they are not close to Zn. And this type of open structure, it can remain in so many conformations. We have written it in this way so that it will help us to understand in easier manner, but it may remain in different conformation, right? So that means, as if in this case, it is already pre-arranged because it is cyclic, it is tight structure, but not in this case. So first A, it has to be arranged in this way so that it can bind with metal properly, then only this chelate formation possible. So that is the benefit if you have macrocyclic ligands. So they are not only multidentate, but because they are covalently constrained to their cyclic form, so they allow less conformational freedom. So it is already having some tight compact structure, pre-organized, better term if you want to use pre-organized. So that is why we are getting more stable complex. Fine. So we will end here regarding all the slides. If there is any doubt. So we are ending here. Thank you for listening.